Thanks, man. So, good afternoon, BruCON. This is my first time here, so it is my tremendous pleasure to be here with you. So, this talk is about browser exploit detection. And so, just to get an idea of the audience, so I'd like to know, how many of are directly or indirectly somehow involved into IDS IPS industry? It could be development of IDS IPS signature or something. Can I see some hands? IDS IPS development? Okay. Oh, so how many of you actually somehow involved into browser exploit development or something? Okay, I see a couple of them. Okay, cool. So I have so this is about me. I'm currently working in McAfee IPS vulnerability research team. So working in information security industry for past 5-6 years. So primarily I was into mostly doing penetration testing of web application and networks. So now I have shifted my focus to vulnerability research, where I'm doing full-time reverse engineering of different exploits and all this. So I'm also into bug hunting and all bug hunting. So I often target Microsoft different MS products, and I, whenever possible, I blog about them. This is my personal blog, and this is my company blog. If you want to take a look, you can refer to these links. So this is the agenda of the talk. So initially, we'll start with brief overview of browser exploits, exploitation techniques, and after that, we'll move to the existing solution we currently have to detect and catch browser exploits. So then we'll slowly move into the motivation behind this research, what motivated me to do this research particularly. So we'll move into TCP live stream injection techniques. So we'll also take a look at the advantages we have over the current exploit detection techniques, and we'll have a few demos. So just to keep the energy level a bit higher side. So okay. So browser exploit. So what are browser exploit? It's actually form of malicious code that actually get delivered to your browser, and it exploits some flaws in your browser and compromise OS security and system security. So it actually targets different components of browser. Browsers are very complex, so it can target different components of browsers. So this exploit codes are mainly written in JavaScript or HTML. So usually it get delivered in form of legitimate web pages. So it could be phishing page or some normal website as well. So this diagram actually shows a very high level overview of browser architecture. So at the top you can see the user interface that we see how the browser looks. And the user interface actually talks to the browser engine. The browser engine then interacts with the render engine. Render engine actually consists of many parts. So this is JavaScript, Flash, XML parser, PDF parser, ActiveX. There are many things. So whenever actually a attacker wants to target any browser or something, he have plenty of options. So among those, the most popular one is he will target these render engines. JavaScript interpreter could be Flash, XML parser, PDF parser, ActiveX. So this also shows the browser attack surfaces. So HTML render engine. So when I talk about HTML render engines, you can consider, if you consider the Edge browser. So the Edge HTML.dll is the HTML render engine for Edge. So JavaScript interpreter is chakra.dll. You can consider this. And there could be many third-party libraries as well that can be targeted. And XML parsers, ActiveX components, Flash, PDF parser. At any component that actually deals with untrusted data. So here actually if we have to divide the type of browser exploits, so browser exploits actually there could be of many types. So on a very high level we can divide it into two parts. So exploits abusing memory corruption. So what happens? Attacker tricks browser to unintentionally modify memory location and violate memory address. Attacker does some memory spraying, that is usually known as heap spraying, to prepare memory layout. And at final stage, the shellcode gets executed, and actually attacker hijack the control flow of the normal program and points it to the shellcode. And there could be also logical flaws as well. And there is no generic technique actually to exploit logical flaws. It completely depends on the anatomy of the vulnerability that the attacker is exploiting. So in this particular talk, we are actually covering this. We will be covering the memory corruption exploit techniques and all this. So on a very high level, if I have to define how attacker actually exploit browsers, so the first part is the exploit delivery. The exploit get delivered into browser, and the next part is the deobfuscation. So attacker usually won't deliver the exploit in a normal. It actually obfuscates the exploit in many ways. So the next part is the exploit actually deobfuscates itself. After that, it prepares the desired memory layout. So in previous slide, we talked about heap spraying and memory spraying. It actually does all these things to prepare the playground, so on which it can perform the exploitation. So next part is the triggering the vulnerability. So in this step, what happens is the attacker actually hijack the control flow of the normal program and redirect the control flow to the malicious codes. And in modern browsers, there are many security mitigations as well. So there are DPASLR techniques, so attacker has to take care of all these techniques. Okay, so this is a example of how actually use after free vulnerabilities are exploited in browser. There can be many vulnerabilities, so I have chosen the use after free to show you how it is done actually. So what is use after free vulnerabilities? So when actually a object is already freed, but it again referenced somehow. So what the attacker will do here actually, this is actually the freed object. The attacker will actually create a fake object in the at the same place where the object was freed, and it will have a fake virtual function table address. The virtual function table address will actually point to a predictable memory location where the shellcode or rope chains are present. So in this way, this entire thing, actually the control flow get hijacked when actually attacker is trying to use after free vulnerability in browser. So now we are going to slowly move to the existing solution currently we have to detect browser exploits. So there are basically three things currently we have. So host-based intrusion prevention system, we also call it HIPS. And other one is network-based intrusion prevention system that actually sits in the corporate gateway or something. And there are sandbox-based network intrusion prevention systems. So in the next upcoming slides, we'll take a deep look. So this slide actually explains how this HIPS or host-based intrusion detection system works. So what it does is there has to be an agent installed in the client system. So the agent will hook different, the process it wants to monitor, and it hooks different APIs. And it continuously monitors suspicious arguments by hooking into those API. When I talk about hooking, it is actually done by, it's called inline hooking. It replaces the first few bytes of the function and replace it with its own code, so that whenever these functions get called, it will first directly go to the HIPS code. So this is a very high-level overview of how a typical host-based browser exploit detection system works. As you can see, this is heap. Okay, so the diagram above actually shows the normal shellcode execution scenario in any browser. So what happens is, suppose the shellcode that the attacker wants to execute is in heap, and the shellcode is actually calling kernel32 winexec. Okay, so in a normal scenario, what happens is that the call to winexec will directly go to kernel32.dll and it executes that code. But when the host-based intrusion detection system is present in the place, what happens is whenever the shellcode is actually calling kernel32 winexec, it will go to the address of kernel 32 winexec. But as you can see, the first few bytes actually replaced with a jump instruction. So what happens is that it will take the jump will actually, the jump instruction actually drop it to hook.dll, which is the DLL injected by the host intrusion prevention system. So it does the various sanity checks on what all arguments are being passed here. So it check if it primarily it is doing two things. It check if the return address is on stack or heap. If it is on stack or heap, then probably it's something is suspicious, because in a normal scenario, it will be, the call will be made from .txt section. So in that case, it will raise an alert based on the checks in hook.dll. So there are many limitations as well for host-based intrusion prevention systems. So there is a very old school technique called hook hopping. So what happens is, instead of directly jumping into the entry point of the function, it will jump after leaving 5 bytes. So it will actually, what you have seen in this previous slide, so it will instead of jumping here, it will directly jump to the second line of the code, so that it is completely bypassing the hook.dll, the code it was about to execute on hook.dll. So this is called the hook hopping technique. This is a very old school technique. So this is one of the major demerits of host-based intrusion prevention system. So it can actually catch obfuscated exploits, but it has a significant impact on OS performance. So it actually makes your computer really slow, since it is hooking different processes and APIs. And also, if you look at from a network admin's perspective, it is very challenging to push updates to all the endpoints if you are managing a very big organization. So pushing new update signature to every endpoint can be very painful sometimes. So now, we have covered host-based intrusion prevention system. Now we are going to take a look at network-based detection systems. So it sits in the corporate gateway, where it monitors all the traffic your organization is actually accessing. So it intercepts HTTP responses, and it simply looks for malicious tokens in HTTP responses. And based on that, it concludes whether any suspicious content is being delivered to user browser or not. So this is a tiny browser POC that maybe for this POC, if anyone has to develop a signature, maybe it will look for this token in a single page. So based on that, it is going to raise an alert, see whether it is suspicious or not. So here is another diagram which actually shows how this actually works. So in this diagram, as you can see, the client is actually requesting a page. So it is actually going through the monitoring device, and the monitoring device actually inspecting the request and send it to the server. And when the server actually responding, so the server actually, again, when the request comes back from the server, the monitoring device actually looking for known malicious tokens in response body of the page, and based on that, it is going to raise an alert whether it's a malicious content is being delivered to user browser or not. So there are obviously limitations as well. Malicious token-based detection system actually doesn't catch obfuscated exploits, and mostly browser exploits we find in the real world are obfuscated and highly obfuscated. So it actually bypasses all this token-based detection system. So, and it also, since we are every day we are adding new signature to the IPS, and it actually significantly it has significant impact on the network monitoring device performance. So it increases latency as well. So, and also there are networks, sandbox-based network IPS, where actually once the content received at the monitoring device, it execute the file in a sandbox environment and check for different behaviors. So the major disadvantage of this technique is, these browser exploits are very much environment dependent. So it is not always possible to, emulate the same environment where the browser exploit is going to work at the sandbox. So most of the time it won't work. So this is one of the major demerits of the sandbox-based detection systems. So now we'll slowly move into the motivation behind the research. What actually motivated me to do this research? So one browser-based exploit actually, since it is mostly written in JavaScript and HTML, so it can be written in thousands of ways. You can obfuscate, you can write a single exploit in maybe 1,000 ways. So it is very, if you are using any token-based detection system, so it is impossible for them to, catch those exploits if it is obfuscated or, written in many different ways. So this host-based IPS also, it is quite good at catching obfuscated exploits, so dynamic exploit, but still it has a significant impact on waste that we have already discussed, what all demerits it has. So what we have seen for host-based IPS, so what we have realized so far that if we can somehow place our code into the client at the endpoint, then actually the code which can actually monitor the behavior of your browser, then we can actually partially or fully solve the problem of detecting obfuscated exploits. What we have seen in host-based intrusion prevention systems. Since our code is already in the endpoint, so we will be able to monitor each and every event that is going on in the browser. So it actually solves the problem. So now the question is, can we do this without installing agent in the endpoint? Yes, actually we can. So now it comes the TCP Livestream injection. So what is TCP Livestream injection? What happens is, suppose you are requesting a normal page from a server. So the monitoring device actually what it will do, it will intercept the request and send it to the server. And when the server is responding back, it is going to intercept the response and it is going to modify the content, and it will send it back to the client. So what response client will receive, it will be a completely legitimate request, but it is modified by the intermediate device that is placed in the network. So where we have seen this TCP Livestream injection actually is used. So we have seen earlier that internet service provider also sometimes use it for black hat advertisement campaign. So they use unnecessary ads into your web pages, legitimate web pages. So you see unnecessary ads there. This is actually not always the Google ads or the normal ads. It's sometimes injected by your ISP. And also I have seen that Wi-Fi router vendors also use this technique to inject ads into your web pages. And it's also used in MITM attacks. So if you are in a local network and someone is performing MITM attack, so one can inject arbitrary JavaScript into your pages, malicious JavaScript into your pages. So this is actually what we have already discussed here. The detection system injects a tiny piece of JavaScript code into the HTTP response page. And the code is actually injected in such a manner so that the injected JavaScript code get executed first. So it is actually injected at the top of the page. So here is another overview of how our detection system actually works. So as you can see in the top of the page, the client is requesting a page that is a GET request that is sending to the server. And in between there is a monitoring device. The request is actually going to the server via the monitoring device. So when the server responds to it, the server send the content to the response content to monitoring device, and what our monitoring device is doing, it's injecting a tiny piece of JavaScript code into the normal web page. So when the client is receiving the page, it is receiving the entire content plus the code that injected by our monitoring device. So if we intercept in the injected web page, this is what we see. This is actually the screenshot actually taken from a proxy. So what you can see here, this is a normal page, and there is a tiny piece of JavaScript code that is injected in the page. So and it is the top of the page. So whenever the code is going to execute, our code is going to execute first. So once the injected code reaches the client's browser, so it is going to do a couple of things. So this diagram actually, on a very high level, it shows what it is going to do. So once it reaches client's browser, it is going to install built-in JavaScript API hooks. It is going to inject. And it will wait for the hooked API to be called. So whenever any JavaScript function is getting called from the page, we are going to intercept the content. We'll discuss all of this in details in later slides. So after that, what happens? We do different checks to detect whether it is whether there is any anomaly or not. I mean, whether any malicious content is being executed or not. And based on that, we'll prevent and block the page from execution. So installing JavaScript built-in API hooks. So as we have already discussed, the injected code is actually at the top of the page. So injected JavaScript code is executed first. That is the hook installation code, basically. The injected code installs JavaScript API hooks. So it mainly hooks JavaScript APIs that are commonly used by browser exploit developers to do various stuffs like obfuscation and exploitation and different stuffs. So once the JavaScript API hooks are installed, whenever these APIs are getting called from the normal page, we'll be able to intercept them and we'll be able to check whether there is any suspicious behavior detected or not. So this code actually shows a very basic how the JavaScript API hooking works. So what we are doing here is we are hooking a alert function. So we are saving the instance of the alert function in real alert function in a variable, and we are actually totally overwriting the alert function. What we are doing, so alert function is actually again calling the real alert function that we have saved here, just to make it more legitimate, so whenever the real alert function is getting called, it looks almost legitimate that that the call is successful. So commonly used JavaScript APIs in browser exploitation. So there are many. So I have chosen a couple of them in this slide. So escape, unescape, there are many string operation related APIs, function involved in array operations. So array push, array pop, new int32 arrays. So document.write, document create element, function involved in ActiveS object creation, and there are hundreds more. So if you have ever taken a look at any browser exploit, what you have seen that this browser exploit, the shellcode part, and many other strings that are actually used in browser exploit in this way. So what we are doing here, we are passing an entire string of malicious code into unescape function, and that is saved in a variable called shellcode. So now if we if our hook is already installed in the browser, so where actually we will be able to monitor the unescape function if it is already hooked. So we'll be able to implement several checks whether this string is actually malicious nature or not. So there are a couple of previous work that has been done on JavaScript hooking. So these are some previous work that actually has used JavaScript hooking to do various stuffs. So now I'm going to quickly jump into a demo where I'm going to show you how this is. So what we have seen here, we are actually this is a normal page without any code injection in it. We are simply calling alert hello world. So for very obvious reason, we got an alert. Now in this page, what we are doing here is this page is actually getting delivered from our detection system in place. So as you can see, the same page actually one IDS.js script is already injected. Now when we call the same page, we load the same page, we see hooked hello world. So it is actually intercepted the content we are passing to alert function and added a string called hooked. So we have already seen one example how this shellcode is being used in any browser exploit. So often browser exploit handles shellcode in this way. So when we have the unescape, here actually it is using the function unescape. So when we have the unescape function hooked into this browser in browser, then actually we can look for different malicious pattern in that string that has been passed to unescape. And based on that, we can detect, we can say that whether the string getting passed to that unescape function is malicious in nature or not. So example exploit detection shellcode, we actually look for many patterns. So these are the opcode of call pop instruction. These are the instructions that actually very often used in shellcode. So these are used for resolving different module based, for example, kernel 32 and all this, some call instruction, nope slates, etc. So we look for all these tokens. We can. So another is spray detection. So this is actually is an immense part of any browser exploitation lifecycle. So to be able to create a predictable and memory layout, the attacker has to spray browser memory so that it can make the browser exploits reliable. So actually we have throughout the process we have reviewed several exploits, browser exploits. And based on that, we have chosen a couple of APIs that has been used very often by the attacker to do memory spraying. One of those is array, int 32 array uncertainty and all this. So this code snippet actually shows how this array function can be hooked to detect memory spraying. So what we are doing here, let's start from line 109. So we want to hook the array function. So what we are doing here, we are saving instance of array in an old array, and we are actually again redefining the function array. So what we are doing here, so whenever the array is getting called, we can easily intercept the argument of what operation is being done, and also we are actually saving an instance of the array whenever they are getting created dynamically inside browser memory. So here what we are doing, we are saving it in a list where whenever the new array objects are being created in memory. So we are also actually, hooking function used to, modify array in runtime. So for example, in browser exploit, what we see that it uses array push, array pop several times to, modify memory inside memory. What we can do here, we are actually hooking array push function. So that whenever attacker uses array push function to modify some array in memory, we can intercept that, so that we will be able to intercept that. So this demo actually shows how we have hooked into array and we are detecting memory spraying. So first what we are going to do, we are going to take a look at the source code. How does it look? So this is a exploit. And it is, as you can see, it is injected with the code is injected by our IPS device. And it is using memory spraying it is calling array function to do memory spraying and stuff. So these are rope chains and shellcodes. So whenever we are actually trying to load the same page in a browser, what we have seen, it is showing that the message actually coming from the code that has been injected by our IPS system, that is showing that malicious JavaScript string detected, flushing the page. Now it has actually flushing the entire page so that the malicious code actually don't get executed in user's browser. So the next thing is you can also actually find certain patterns when return-oriented programming is used in browser. So if you see any rob gadget, so what you will be able to figure out a certain patterns, because all these addresses are taken from a single module. So what happens is the most significant byte will always remain same. So once the function, the system injected hooks are in place, we can do several checks to identify whether the string is being passed to the unescape function is rob gadget or not. Is it is whether attacker is trying to do any return-oriented programming to exploit the browser or not. So this code snippet actually shows how we can actually use this, this return-oriented programming patterns. So also sometimes what we see that attacker can create element dynamically. So there are many ways you can actually an attacker can create dynamically content in a page. So what we can do here, what the attacker has option, attacker can use document.create element to create element in the page, or it can use document.write. In the next slide, what we are going to see how we can hook this create element or document.write function to intercept whether any suspicious elements are being created in the page or not. So here is an example of dynamic how we can hook document.write function. So what we are doing, we are almost doing the same things. So we want to hook the write function. So this is the document underscore old is actually saving the old instance of the document object, and this write old function is actually saving the old function, the write instance of in old write old. So what we are doing here, you can implement several checks to find out whether this any suspicious content is being written to the page or not. So, and we are actually finally what we are doing, we are returning the actual object that has been the attacker is trying to add in the page. So we have also seen in the past that attacker can use different ActiveS object to detect whether it's any detection device is already in place or not. So this example actually shows how this ActiveS object hooking can be done. So this is actually also pretty straightforward. What we have seen earlier, we are actually simply hooking into ActiveS object function, so that we'll be able to intercept what element or what document object ActiveS object is trying to create in the page. So what we have seen so far, we are trying to hook into the built-in JavaScript API, JavaScript built-in APIs. So what we have to hook into custom the function that has been defined by the attacker. So if you want to hook them, what you can do? So we have developed a system that actually can somehow manage to hook into custom functions as well. So in this code snippet, what you can see there is a function that is defined here, function myfunc, and it is taking two arguments, argument 1 and argument 2. So when the detection device is in place, what it does is it injects a one-line code into it. So here what it is doing, it is injecting scanarg and arguments. The arguments that it is getting passed to this, it's actually holding an array of all the argument that is being passed to myfunc. So what happens here is the scan argument function is defined in the ids.js, which is here. So whatever argument is being passed to the myfunc1, it is going to go through all the checks we have implemented its scanargs, so which is defined in ids.js. So in this way, we can actually hook into custom function that is defined by attackers. So what we have seen in previous slide, that there is a function scanarg that is defined here. So this is how the scanarg function looks like. So it is actually taking the arguments, and the argument list, we can then iterate through all the arguments and implement checks here whether the argument getting passed to the function is malicious in nature or not. So this is all about hooking custom functions. So this demo actually will quickly show how this custom function hooking works. So what we can see here, see, there is one function and it is taking size and padding 2 arguments. So these are the things that we are going to pass to the function, that is name is totally random, we are passing to it. So this is a normal page where no code injection has been done so far. So this page we are seeing here is actually coming via our IPS system. So what we can see here, it has injected a tiny line of code, it is scan args, and it is passing all the arguments to it. So when we load the page, actually what you have seen, the arguments that we are passing to it, this code actually, this is printing here. The hooking code we have injected, it is not doing any checks that we do in IPS, but it is simply printing those arguments. So this example actually to demonstrate how this custom functions and their argument can be intercepted. So these are the arguments that we have seen in the console. So also we may have to, inspect the variables that are actually defined in global space in any page. So we may have to, inspect strings that are actually, defined as globally as a page. So to be able to inspect strings that are actually declared as a global variable, we have a technique that looks something like this. We have to inject this code into any script blocks. What it is going to do is it actually in the global execution context, this refers to the global object. So from this actually you can iterate through this object, and you can actually enumerate all the variables that is declared in global space. So we are doing exactly the same thing over here. We are actually iterating through this object, and actually we are calling a scan global variable function. So what this function is doing, it actually does several sanity checks to find out whether any malicious content is defined in global space of that page that we are inspecting. So this function is actually doing the same thing, scan global variables. So we also have a demo for this. So as you can see, there is an obfuscated string that is declared here as a globally in the page. And this is a normal page. There is no code injection that has done so far. So this is the page, where this code injection has been done by the IPS device. As you can see, it is, and this code is also injected into the page. Now we are going to load the page in browser and see what happens. The injected code actually simply prints the strings. It tries to print the string that has been actually defined globally in the page. So what you can see, the my obfuscated JavaScript string. So it is actually printing everything in the console log, which was actually defined in the global space. So there are many anomaly detections codes as well. So what we can do here is suspicious. We can look for suspicious API call sequence. Maybe we are, browser exploits. What often we see is it calls array or unescape or escape functions very aggressively. So we can, implement different anomaly-based checks to detect whether any malicious attempt is being made against browsers. So unusual API call count also we can verify. So as I have already told, for memory spraying and all this array functions get called aggressively. So this unusual API call count, if you are actually, monitoring it, how many times this array functions or unescape function is being called by the page, we can actually detect some, anomaly, whether any malicious content is being delivered to browsers. So what we have seen so far, so we have to combine everything together to make a decision whether the subjected page is malicious in nature or not. So we have some code which is actually checking whether shellcode is in place, spray is being done, is there any rope chain or not, and there are other anomaly-based detection systems. So based on all this decision, we have to make a final decision whether the page that we are actually inspecting is malicious in nature or not. So this decision is done by the outcome of all the checks what we have seen so far. So once we have decided that the system has decided the page is malicious in nature or not, right now what we are doing here is we try to grab as much as content as possible and we'll save it in a remote logging server, so that it can be inspected later whether it's a false positive or not, and then we'll actually flush the page using this window.location about blank. This is going to flush the entire page so that exploits don't get executed. So once the system was in place and we wanted to test it against real system, so it was actually initially it was a complete disaster because there were many false positives. It was detecting a normal page as an exploit. So we have done a pretty lot of effort to make the systems smarter. So what we have done so far actually. So this I have already told. It was actually when we tested it, we faced a lot of false positives and it was breaking a lot of legitimate web pages as well. So so for that actually we have developed an automation system. So by using which we will be able to closely monitor how certain pages are being handled by our detection system. So what we have done so far, we have set up a couple of systems where Internet Explorer was running. The pages that are with the entire traffic was actually passing through the JavaScript injection proxy. So whenever we are actually loading any page from normal internet, it was injecting a code into it. And in the hooking code, we are actually inserted, there are a lot of logging functions into it, so that we can actually closely monitor how each lines get executed in a page. And if there is any false positive, we can later verify why the false positive has appeared, what went wrong actually. So these are the logging routines that we injected in page. So regarding that logging routine, how it was done, actually we injected a tiny piece of DLL into Internet Explorer. So this Internet Explorer actually hooks into this function called JScript 9, JS Math 8 and 2. And what all arguments we passed into that function so that we can log that in a text file or log file. So this is the logging routine, how that logging was done. So what we have found after this entire automation project and testing. We have seen that when we tested this against Metasploit framework, so it was actually able to catch most of the Metasploit exploit, just because. So we see that in Metasploit, if you take a look, there are this unescape function, escape functions are aggressively used. So they actually do some effort to, obfuscate exploits, but still, they aggressively use this unescape function and escape function. So those API hooks actually was able to catch all those exploits. So Metasploit exploits. And this array hooking routine actually proven to be the most successful one and the most powerful one, because we have also tested the exploit detection system against some exploit found in the real world. So the browser exploits cannot be written without doing memory spraying. And for memory spraying, this array hooking, this function has to be called, this array and unsigned integer 32-bit array. So since our system actually hooks into this array related functions, we are easily able to catch some of those exploits that were actually found in the wild. So, and as I have already told, there are some heuristic-based checks also that actually counts, that actually detects aggressive API call. Those exploits also, those checks also were quite helpful in some places. So where we'll be able to, detect some real-world exploits. So as you have already realized so far, that the main idea of this entire detection system is injecting JavaScript code into the page. So yes, we can actually use this system as a browser plugin. So browser plugin has the capability to inject arbitrary JavaScript code into web page. So yes, we can, but actually this doesn't solve the problem of since we are also trying to solve the problem of without installing any agent in the endpoint, so it reopens the problem of installing the agent in the system. So dealing with HTTPS, there are already, it's a very common technique that used by IPS vendors to decrypt HTTPS traffic. So what they do is they install a the root certificate in every endpoint, and what they do is whenever the client is sending any request, the client encrypts it, the inspection device actually decrypts the traffic, and it does several checks to figure out whether the request or response is malicious in nature or not. It re-encrypts the traffic, and the web server actually then decrypts the traffic, and the response comes in this way. So we can actually implement the same thing in this system as well, where actually it will be able to inject code into HTTPS traffic as well. So now we'll jump into the advantage the system has over current signature-based detection system. So it is obviously what we have seen, it is quite generic in nature. It is not actually any token-based thing. So we are not looking for malicious token, malicious JavaScript code into page. So, and since the code is actually, when we are detecting the exploit, the exploit is already deobfuscated itself. So what things we are getting, we are actually inspecting the deobfuscated exploit code. So this is obviously a generic exploit detection technique, and this is and also an agentless. What we have seen so far, that there is no agent required to be installed in endpoints. So this is a agentless solution. So it actually also improves network monitoring device performance significantly, because what we can see here, it actually distributes the entire load to the different browsers. So in normal IDS IPS, what it does is it actually checks whether any web page has malicious content in nature or not by looking for various tokens in the web page. But here what we are doing here, we are simply injecting a tiny piece of code in the IPS device, and later the rest of the part is left upon the browser. So browser is going to actually do the main things to identify whether it is malicious in nature or not. So it significantly improves network monitoring device performance. So it is since the backbone is written in JavaScript, so it is obviously platform independent. So JavaScript actually runs in almost all the platforms. So you can consider mobile device, Mac, Windows, Linux, whatever you can take, whatever you want. But this system is going to work. So it is obviously a platform independent system. So as I have already told, the shipping update to each and every endpoint is a big challenge for network administrators. So for this case, actually, the update shipment is quite easy. What the administrator has to do, it has to push the updates to the the monitoring device only, and the monitoring device actually is going to deliver the update automatically to the each and every endpoint via the web pages. So it is quite easy to ship updates. So some limitations and bypasses. Yeah, there are, since we are actually using JavaScript and JavaScript to, tinker with the web pages, and JavaScript is pretty powerful. So this is actually, it has some limitations as well, and there will be bypasses definitely. So I came to know about this anti-JavaScript API hooking technique, and when I discussed with my colleagues, so they actually suggested many techniques that can be probably used to bypass these techniques. So anti-JavaScript API hooking techniques and some anti-JavaScript API hooking. So, and actually this fight is going to continue, since one defensive mechanism comes in, and so there will be some technique to bypass those. So this is going to continue, obviously, and there will be there will be bypasses. So so I am going to close this with since the endpoints are becoming more and more powerful every day. So what we are doing here in this system is actually we are distributing the most of the loads to the endpoints, and the endpoint is becoming more and more powerful. So this actually reduces the network latency significantly. And since JavaScript is the backbone of our system, it is obviously very powerful language, so it gives a lot of it gives the defenders a lot of power to closely monitor closely monitor how the exploit codes are being acting in browsers. So, and also on the other hand, it gives attacker also a lot of power to overcome different security measures. So now I am going to show you a demo of a real world exploit that actually I have taken from VirusTotal. So when the exploit detection device is in place, how it is going to. So what we have seen in earlier demos, this is the same thing. So this is the URL of the direct traffic, and whenever we are accessing it through port 8888, it is going to come via our IPS system. So first thing first, what we are going to see, we are going to take a look at the source code. How does it look? We are actually verifying how the code actually looks, the exploit code actually looks. So as you can see, it is completely junk. It is a highly obfuscated exploit. And there is no code injection has been made so far. So now this is our, enter traffic is coming from our IPS device. What we have seen, code, tiny piece of code is injected here, ids.js, and there are also some other code that is injected by the monitoring device. So now we are going to run this exploit in a virtual machine. So since it's a real world exploit, what it is going to do is we are going to show the successful exploitation by showing the DNS request the exploit is making to the malicious server, so that you can see the Wireshark window that is open. It's a Firefox exploit, by the way. This is, here we are loading the actual exploit, no injection, with no detection device in place. So we are sniffing the traffic, and we are interested in DNS only, so only DNS filter is applied. So we have clicked on that exploit. Let's see what happens now. So what we have seen some activities in Wireshark. So now let's take a look. As you can see, it is trying to make some DNS call to some servers. So if we Google that, what DNS call it has made. So as you can see, actually these are all infected server, and it is all listed in malware domain list and all this. So what we have realized so far, that obviously the exploit was successful. So now what we are going to do, we are going to, when the exploit detection system is in place, how does it look? We'll take a look at it. We have clicked on that link. So what you have seen, that it has said that malicious string has been detected. So it has blocked the entire exploit, and at the same time we didn't see any DNS entries. So the exploit was obviously failed. So this actually demonstrates how this exploit detection system blocks real world exploits as well. So there are few major references. These are the major references. So, and also, here I'm going to end my talk. So if you have any question, you can shoot it up, or I'll be around. So if you have any, you have any doubt you want to clarify, I'll be happy to discuss over a cold one. So thank you very much.